Howdy, y'all. So as TD said, name's Cody. I work for Kixer. We do mobile ad optimization. So if you're an app developer or a website publisher, come talk to me after this. Kafka is pretty much the backbone of our infrastructure. And yeah, go Kafka. So the existing Kafka integration in Spark 1.2 didn't really meet our needs. So I wrote one that did, contributed it back to Spark, and it's been available since Spark 1.3. So you'll notice that the title of this talk says exactly once. Usually if somebody says exactly once about a messaging system, they're trying to sell you something. I'm giving away code for free, so I don't have any particular incentive to mislead you. So I'll make it clear up front, I'm not literally talking about how to read each message only once from Kafka in a distributed system with failures. What I am talking about is how to read messages out of Kafka, do whatever your transformation is, and save results in such a way that the results you get in your data store are the same as if each message was processed exactly once. So if you're disappointed I haven't solved a fundamental distributed systems problem, you probably have time to find another talk. All right, so one slide review of Kafka. I hear people talk about Kafka as if it was a message queue. Thinking about it that way will lead you astray. It is an on-disk circular buffer. So as messages get produced into Kafka, they get written to files on disk. As the amount of disk space you've allocated fills up, oldest files get deleted to make room. There is no queue that messages are being popped off of in response to consumers reading them. Now, it's not just one big buffer. It's split up into topic partitions. Those are just folders on disk, and those folders may be on multiple machines, so you get some parallelism and some redundancy. When I'm reading from Kafka, I do so based on an offset. An offset is just a per topic partition count of messages since the creation of that topic partition. Right? So I may say, hey, Kafka, I want to read the sales topic, partition 2, messages 200 through 300. And then I can go read messages 300 through 400, or I can go back and read 200 through 300 again. Or I can skip forward and read 1,000 through 2,000. As long as those messages are still in the buffer, I can read them in whatever order I feel like. It's up to me to keep track of what messages I've successfully read. That means that delivery semantics are fundamentally up to me. So when we're talking about delivery semantics, there's two kinds of state we care about. One is offsets, one is our results. So if we try saving our offsets and then saving our results, when there is a sudden but inevitable failure between those two operations, there are some messages for which you never save results. The fact is the messages get lost. Try things the other way around, save your results first, then save your offsets. When you get a failure, the effect is some messages get repeated. Now you'll notice the central problem here is you've got two different kinds of state that are getting out of sync. Because of this, a Kafka consumer on its own can't just have some magic config option to give you exactly once semantics. It has to know something about how you're saving results. So if all I'm going to give you is at least once, how do you make that look like exactly once? There are basically two tricks for that. One of them is idempotence, the other one's transactions. So idempotent, fancy word for an operation that's safe to repeat. So hypothetical example of this. Let's say I have discovered that consumer app purchasing behavior is highly correlated to hair color. So I have this Kafka topic full of messages where they're keyed by somebody's Android device ID, and the value of the message is a photo of that user. And the transformation I want to do is analyze the photo, figure out their hair color, and store it in some key value store, say Redis, right? So my key is going to be Android device ID foo. My value is going to be hair color red. My job dies in the middle, and I reprocess that message. My message didn't change. It's going to have the same key and the same photo. My transformation is a pure function. I'm going to get the same result. So I'm going to save the same result for the same key, and it is as if that message got processed exactly once. So this is nice work if you can get it. Anytime that you've got a transformation that is essentially a map, you should be thinking about idempotence, because if you've got 100 messages in, 100 results out, it's probably fairly clear how the key for the first result is derived from the data in the first message and so on. Things aren't always that easy, so another hypothetical example, let's say I've got a Kafka topic with all of my sales records in it, right? So my key is a website ID, and my value is the amount of money I made off that sale. And the transformation I want to do is keep a running total per website of how much money I'm making. So that's more like a fold, right? So that's more like a fold. I've got 100 messages in and like 7 results out if I've got 7 websites. And it's not entirely clear how I come up with some key for the first result that was derived from the 15 messages that contributed to it. The other thing is I'm probably doing destructive updates to my database, right? I'm like incrementing sales. And if that happens multiple times for one message, I'm going to get the wrong result. So what do I do there? Transactions. I go ahead and calculate my results outside of a transaction. Then I start a transaction, save my results, save my offsets. Then I make sure my offsets are OK. And by OK there, I mean if the last offset I had saved for this particular topic partition is 100, my batch of messages better begin at 101. If it's higher than that, something got skipped. If it's lower than that, something got repeated. And in either case, I need to roll back the transaction. As long as I roll back whenever there's a failure or anything weird happens, my offsets and my results stay in sync. It's as if each message is processed exactly once. So upside of that, works for any transformation. Destructive updates, as long as they're destructive updates to the same data store, are fine. Downside is it's more complex. You got to have a transactional data store. Notice I didn't say you have to kill all your parallelism because you only have to hold the transaction open long enough to save your results. So everything we talked about so far is just kind of basic physics of Kafka that apply regardless of what software you're using to consume from it. So the Spark situation in 1.2 was based on this idea of long-running receivers and a write-ahead log. So a long-running receiver is a Spark task that lasts as long as your job lasts, that runs a Kafka high-level consumer that reads messages from one or more topic partitions and periodically commits offsets into Zookeeper. Now, if you have your job die while there are messages in flight that have already been committed into Zookeeper, you're going to lose data. So what you can do about that is turn on a write-ahead log. The idea there is messages get pushed into HDFS, durable storage, before they get committed into Zookeeper, so that when you start back up, you can get those messages out of there. Good thing about this is that it could potentially work with message sources other than Kafka, as long as there's some way to acknowledge a message. Downsides. So because of the way receivers are designed, they're scheduled as if they occupy a core regardless of how much work they do, right? So if I have a topic that's important but doesn't have many messages, chances are the node it's running on isn't going to be doing as much work as it should. If I have a topic that has a lot of messages coming through it, we've got to manually create multiple receivers and then union them together, and it's kind of awkward. The other downside is, if you think about it, Kafka is a write-ahead log, so we're doing duplicate writes. And then finally, all of this only gets us at least one semantics, right? Because Spark output operations can fail and be retried, you still got to deal with that, which means if you want exactly one semantics, you have to use idempotent writes. You don't have the option of doing transaction writes because the API doesn't give you access to the offsets. So I looked at this situation, I said, well, we need some parallelism. Kafka's got parallelism. We need a durable data store. Kafka is a durable data store. Why don't I just expose that directly? So as I'm implementing a D stream, right, it's basically just a sequence of RDDs. And as I'm implementing an RDD, two most important methods are how to split your work up into partitions and then how to actually compute the value for a given partition. So in the case of this Kafka RDD, the definition of a Spark partition is just a Kafka topic partition plus the beginning of an offset range and the end of an offset range. And when I go to compute that out on the executor, all it's going to do is connect to Kafka, pull exactly that range of messages directly from Kafka. Nice thing about this is once the RDD is created, it's stateless. If the job dies, if the executor dies, some other executor just picks up that partition, pulls exactly the same messages. As long as they're still available in the buffer, of course, you get the same results. And you can use this interface as a batch RDD like that if you want to. There's an interface for that. For the streaming case, what the driver is going to do is keep track of the offsets in the last successful RDD. And when it needs to go schedule the next RDD, it's going to connect to Kafka and just ask about the highest available offsets. It's not pulling messages. It's just saying, hey, what's your high watermark? And then the next RDD that it schedules is going to span that gap between what was done and what's available. So good thing about this is your parallelism model is really straightforward. One Spark partition corresponds to one Kafka topic partition. There's no more duplicate writes because you're relying on Kafka. And the API is going to give you direct access to the offsets. You can use either idempotent or transactional, whatever works for you. Downsides. It's specific to Kafka. If you don't want to hear the word offset, go use something else or don't use Kafka at all. If you don't want to spend money on Kafka disk, don't use this. If you only allocate 4 hours worth of Kafka storage and your job fails overnight, when you wake up in the morning and start it back up, you're going to get an offset out of range exception. You're going to lose data, and I'm going to say spend more money on disk next time. Even if you don't care about any of the semantic stuff, this may be worth checking out for you if you care about server costs. This is a graph of our CPU utilization before and after switching to the direct stream for one particular job. As you can see, previously, there were some nodes doing a lot of work, some nodes not doing much work. Afterwards, much more even overall usage. So this all sounds good to you. How do you use this thing? Okay, wall of code. If you're worried about wall of code, don't worry about it. Just listen to the concepts and go look at the GitHub later. So important things about using this API. You're going to give it a map of Kafka configuration parameters and a set of topics you're interested in consuming, and it's going to give you back a stream of key and value for each message. From a delivery semantics point of view, the important thing here is this auto offset reset. So if I set that to largest, that's the highest available offset, the most recent message. So if I start my job back up after a failure, and there are any messages that came in while my job was down, they're going to get lost. Again, this isn't strict at most once semantics because you still got output operations that can be retried. If I set it to smallest, the oldest message in the buffer, I start my job back up after a failure, I'm going to get at least one semantics, but that's going to come at the cost of replaying my whole buffer. Now, for my hair color hypothetical example, maybe that's fine, right? Like maybe I don't get a lot of messages in, or maybe it's pretty straightforward to figure out hair color. If that's all I want, great. If I want finer grain control, I have to store the offset somewhere. Two choices for where to do that: Spark checkpoints or my own data store. If I want to put them in a Spark checkpoint, most of the work's done for me. The offsets, not the messages, just the offsets, get stored in the checkpoint and provided when the job starts back up from the checkpoint. Downsides of this are, because remember, for transactional, you got to put the data and the offsets in the same place. You're probably not storing your results in your Spark checkpoint, so you can only use idempotence. The other downside is that Spark checkpoints aren't always recoverable. Typically, this is because you've upgraded Spark or upgraded your code. Your own data store. Downside is a little more complication. There's a little bit of code you have to write. Upside is you can do idempotent or transactional, and the question of whether the job's going to recover okay is entirely in your hands. Spark checkpoint, blah, wall of code. That's a direct copy paste from the docs. Just follow the standard Spark docs for the checkpointing, and if you're doing something that looks like my hair color example, that's all you need to do. Do your idempotent right, and away you go. If you're doing things in your own data store, you got to use a slightly more advanced form of the API. So the things to look at here are, instead of just providing a set of topics to consume, I'm providing a map from a particular topic partition to the exact offset to start that stream at. And I'm just using a data literal here so that you guys can see what the shape of that argument looks like. In real code, that would be, select from my database where topic partition is in the set of topic partitions I care about, and my job identifier is this. Give me those offsets, turn them into this map, provide them the API on startup. The other thing you'll notice here is that there is a message handler function that you can pass in. What that allows you to do is get whatever particular pieces of the Kafka message and metadata you want to end up in your stream, right? So for this trivial example, you'll see that the type of the stream is an input dstream of int, because the result of my message handler function is just the message length, right? So the question of if I'm providing those offsets on startup, I had to have gotten access to them somehow, right? How do I get access to them? So I can use that message handler function to get access to offsets on a per message basis. Why might I want to do this? For my sales topic example, let's say in addition to saving this kind of aggregate per website count, I'm also saving individual sales records into my database. If that's what my job is doing, it may make perfectly good sense for me to deal with offsets and results on a per message basis. And if that's the case, this API gives you access to everything that Kafka would give you, So it's no problem to do that. If I'm really just concerned about the aggregation case, that may not be the most efficient way to do things, right? I would want to be able to do something in more of a per batch basis. So what I'm going to do here is, as I'm processing each RDD, I'm going to cast it to this interface that has a method that gives me back an array of offset ranges. There's going to be one entry in the array for every partition in the RDD. And that each entry is going to have, the topic, the partition, the beginning of the offset, the end of the offset range, right? So I get that on my driver. I go ahead and use normal Spark methods to do whatever transformations I want to do on my RDD. I collect my results back to the driver. And then on the driver, I am saving all my offset ranges and all my results for that particular batch inside a transaction. I'm not going to go into the details of what my save batch does because it's probably specific to your database. And again, if you want a working actual example of this, check the GitHub link. Important things to notice here if you're having wall of code reaction is that I'm doing things per batch. My results are being calculated in parallel. My results are being saved on one node. This is probably where you want to start at first for most kinds of jobs. If I want to try and get some more parallelism during writing, one way to do that is to get access to offsets on a per partition basis. So when would I do this? Let's say that, again, for my sales topic example, that when I'm producing messages into Kafka, I've already keyed them such that all of the sales for a particular website are going to the same partition, right? If that's the case, I can do my aggregation on a per partition basis. I don't actually need to do it across all topics. So if I know I'm doing this, I can go ahead and do the same typecast on the driver to get my array of offset ranges. And then as I'm processing each partition, I'm going to index into that array using the Spark partition identifier. And again, this is safe to do because there's a one-to-one relationship between Kafka partition and Spark partition, and they're in the same order, right? So that gives me my offset range just for the partition that I'm working on. I then go use Scala methods on this iterator of messages to do whatever my aggregation is, get my results for that partition, and then I'm saving messages on the executor for that particular partition along with the offset range for that particular partition. The thing to be aware of here is that the reason this is safe is, again, because of this one-to-one relationship. If I do some kind of Spark operation that incurs a shuffle, it's going to repartition things, and it's no longer safe to rely on that partitioning, right? So what I am not saying here is that, oh no, as soon as I do a shuffle, I can't use the direct stream API at all. Not what I'm saying. What I'm saying is, if you're doing a shuffle, A, you need to think about what you're doing, and B, you need to think about either using the per batch approach or the per message approach. All right, so as I said, GitHub link there has a fairly detailed blog post with more information about the internals of the implementation, as well as a fully runnable project. Let's go ahead, and we've actually got a pretty decent amount of time for questions.
Hello?
Yep.
Hi, with the offset approach and this direct API, does that help in any way with flow control or back pressure when you can suggest an offset range that you want? Or?
Okay, so there's kind of two things when you talk about back pressure in Kafka. One is that Kafka itself is not designed to provide back pressure, right? So if you're talking about back pressure producing into Kafka, that's not what Kafka is for. Kafka is to take whatever fire arrows you give it and handle it. If you're talking about back pressure from Spark to Kafka, again, Kafka is a pull mechanism, so it's not literally back pressure. So sorry to be pedantic, but to actually answer your question, if you're concerned about overloading your workers, there is a configuration parameter for the maximum number of messages per partition per second that you want to process. So that usually takes care of that concern.
It doesn't appear to me that the Java API is in sync with this new direct thing as far as has offsets or Kafka RDD.
So the Java API Java is Java, and has offsets is an interface, so just go ahead and do the cast.
Yeah,
On
but
the
the Java,
Python side,
let me just say that the guy doesn't implement that interface.
so to be clear, a Scala trait is a Java interface. A Scala trait with no methods on it, or excuse me, with no state on it, is a Java interface.
We can talk after.
Yeah,
but
we can talk
sure
after.
Sure, it's not right.
Sure. If you're talking about the Python API, yeah, there probably is some catch up to do there.
Kafka stores its offset usually in Zookeeper. Is there a native integration with Zookeeper storage?
So this API is completely agnostic as to Zookeeper. It's not going to put anything into Zookeeper for you. If you want to put something into Zookeeper for whatever reason, whether that's because you're using Zookeeper as the system of record for your offsets, or because you're just using Zookeeper to play nicely with other Kafka tools, either way, you have the offsets, you can put them into Zookeeper if you want to, right? There is code in the project to make that process a little bit nicer. It is unfortunately private currently. I personally would like to make it public, so if you want to take a look at the API, see how it works out for you, the name for the file is kafkacluster.scala. Take a look, tell me what you think.
Any reason for not storing offsets in Kafka itself, as Kafka itself does?
So Kafka itself isn't transactional. And as long as that doesn't bother you, you're welcome to go ahead and store offsets in Kafka. And that Kafka Cluster API should let you do it fairly straightforwardly, as long as you go set out private Spark out of it and rebuild Spark.
Hey, can I increase or decrease the parallelism based on the volume of messages flowing in?
So it depends on what you mean by decrease or increase parallelism. If you're talking about increase reading parallelism, the way to increase reading parallelism from Kafka is to add more partitions to Kafka. If you're talking about increasing parallelism down the line in your transformation with something you're doing in Spark, like, yeah, you can repartition however you want to in Spark.
Thank you.